Hello everyone, welcome to GATE Pass. I am Dr. Poonam Nigam and I am starting this channel which is completely devoted to GATE in chemical engineering. So what I will do is I will solve last 20-year papers on this channel and I will be doing it subject wise. So the first subject which I have picked is thermodynamics, and in a series of video what I will be doing is, first of all I will be solving problems which appeared in year 2022. Okay, so I have picked up for this video two problems. First of all, I will teach you the concept and after that we will come back to the problem. So the concepts which are required, let's just quickly brush through them. Okay, so you know that U is a function of S, V and N. Okay, and you might have also seen this equation that du is equal to TdS minus PdV plus mu dN. Okay, this is a fundamental equation. It contains all the information which you need for the system. Okay, so that's why this is known as a fundamental equation. This is also known as Gibbs equation. Okay, now since u is a function of S, V and N, I can also write du as in terms of its partial derivatives like this. Okay, if I compare these two equations, what I find is that del u by del S at constant V and N is equal to T, del u by del V at constant S and N is equal to minus P, and del u by del N at constant S and V is equal to mu, that is chemical potential. Okay, so keep this in mind, this will come later on. Okay, so we have u which is a function of S, V and N, but for some applications or for some processes you need a different set of variables. Okay, so I might need like say T, V and N or S, P and N or T, P and N. Okay, so I want to derive equations involving these set of variables. Okay, but still I don't want to lose any information. Okay, so from this equation I want to develop equation for, let's say, another function which is A. Okay, which is a function of these variables. H, that is enthalpy, it is a function of these variables. So I want to now come up with equations which are in a sense they are also fundamental equations because they are equivalent to this equation. Okay, so let's see how you change the variables. Usually it is done within a mathematical framework which is known as Legendre transformation. So we will quickly within 2 minutes study what is Legendre transformation and then come back and see how you end up with the equations for these variables. Okay, so you know that any curve, okay, it can be given as, in an xy plane I can write any curve y. So the equation of that curve can be given as y, which is a function of x. Okay, an equivalent way of giving the equation of this curve is, what I can assume that this curve is bound by a set of tangents. Okay, so if I give an equation of all these tangents at different points, then equally well I can define this curve. Okay, so I have drawn several tangents and this curve can be given as a set of tangents. So let's say that this tangent, it is at some point xy. Okay, it makes an intercept with the y-axis at psi. Okay, and it has a slope which is p. Now the slope, it is usually given as dy by dx. Let's try to find out what is the slope. So for this equation I need 2 points to write the slope. I have 2 points, right? So I have written the slope p is equal to y minus psi upon x minus 0 because x is 0 over here. Okay, now if so what I am basically doing is I am writing it as psi, which is a function of p, and trying to eliminate x and y. Okay, so you can also write x and y in terms of p and you can come up with an equation psi which is a function of p. Okay, now both these are equivalent ways of giving the same curve. Okay, now let's see what is psi then. If I rearrange this equation, then I come up with psi that is equal to y minus px or y minus dy by dx into dx. Okay, so this is my Legendre transformation. Now let's see how I apply Legendre transformation and come up with the definition of these three energies which we have defined. Okay, so I will just, I should not have erased it. Let's see, let's have another curve. Now I am saying that, okay, this is u which is a function of let's say S, and now in this case what I am doing is I am keeping V and N constant. Okay, let's take another plane in which what I am doing is, let's say I am plotting U as a function of V, and in this case I am keeping S and N constant. Okay, now let's apply the Legendre transformation for this case. Okay, so what I am saying that I am defining a function psi, let's call it right now A. Okay, and that is equal to y, which is nothing but u. dy by dx is del u by del s, okay, at constant v and n. So I write del u by del s at constant v and n, multiply with x, which is s. Now come back over here, what you have, del u by del s at constant v and n is nothing but t. Okay, so now I have come up with the definition of A, which is A is equal to u minus ts, which I am going to write over here. Okay, now let's see this case. Now I am doing Legendre transformation with respect to V. Okay, so let's again write. Now I am defining another function. I will call it as h. Okay, again your y is u. dy by dx is what? Del u by del v at constant s and n. Okay, and that is multiplied by x, which is nothing but v. Okay, now del u by del v at constant s and n is nothing but your minus p. So I put it over here and I get the definition of h, which is u plus pv. Okay, so you see that these equations which you have learned by heart till now, that h is defined as u plus pv. Now you know from where these equations are coming. Okay, here I am doing a partial Legendre transformation. Okay, I am just doing the Legendre transformation with respect to one variable only. If I do Legendre transformation with respect to both the variables, then I come up with the function g, in which I have replaced s by t, v by p. Okay, and that comes out to be a combination of these two, u plus pv minus ts. Okay, you can do the Legendre transformation and see it yourself. So that's how now I have got three different energies. Okay, A is equal to u minus ts, h is equal to u plus pv, and g is equal to u plus pv minus ts. Okay, and all these are equivalent forms. Okay, now let's derive a differential equation for these, and then you will see how they are function of t, v and n and everything. That will become more clear when I write it in a differential form. Okay, so let's say dA, that is equal to du minus d of ts. It's not comma. Okay, so that is, what is du? Du is equal to tds minus pdv plus mu dn. Okay, tds minus pdv plus mu dn minus tds minus sdt. tds gets cancelled and I am left with minus pdv minus sdt plus mu dn. Okay, so this is dA. You can do it for enthalpy as well as Gibbs free energy, and you can come up with the same form of equation which I have derived for A. Okay, but when you are in an exam, you do not have time to do all this differentiation, substitution, etc. So I will just quickly tell you how I do it. Okay, so this equation is easy to remember because you see it several times. Okay, whenever you try to write first law, you write this equation. Okay, so this equation you remember by heart if you have studied thermodynamics. From this I will tell you how you can quickly write these equations. Okay, so for dA, what I will do is I will remember that I am replacing s by t. Okay, so I will go to this equation, I will just switch the variables. I write s dt, and when you switch the variables you just put a minus sign over there. Okay, so that's how I quickly write all my equations. So I don't have to differentiate and see all the times. Let's just do it for dh. So in this case, in h you are replacing v by p, other two variables remain the same. So I'm going to write the same things, tds mu dn, but these will be switched. So I will write v dp and change the sign. Okay. Similarly, dg, my short form is, I will switch the signs of these two, and TDS will become SDT and PDV will become VDP. So I am quickly getting my TDS will become, okay, SDT, that will be a minus sign, plus VDP plus mu dn. Okay. So these are the equations which I can write quickly if I remember this equation. Okay. Now, once you reach this equation, another thing which you need or which you derive from these equations are Maxwell relations. Okay. Several people remember writing Maxwell relation using mnemonic square. You might have seen that some U, G and whatever they write. I don't remember. Usually I forget the sequence in which you have to write, the direction of arrows which you make. So usually there are chances you might make an error if you remember it this way. So how I write is, I just take the equation, okay, and you might have studied, because I am going to follow the book Smith and Van Ness, okay. So there you can go and read it in chapter 6, I think. How do you come up with Maxwell equation? You apply criteria of exactness, then you take derivative twice and then you equate those derivatives and come up with Maxwell relation, okay. But I am going to write the Maxwell relation seeing these equations, okay. So let's write Maxwell equation from this equation. So what I do is, I take partial derivative of t with respect to, let's say, one of the variable, let's say dv. Now you will keep the other two constant, so I will write Sn n is constant, and that is equal to, let's shift to this coefficient. So I will take a partial derivative of p. Now I will take it with respect to s and keep v and n constant, okay. So this is a quicker way to write your Maxwell relation. No need to remember that square, and without error you can write it, okay. Similarly, from these I can write the Maxwell relation. Let's say minus sign, s will become del s by del v. Okay, so yeah, of course there will be a negative sign over here. Now we were deriving the Maxwell relation using a, so it is minus del s by del v, that is equal to, again, minus del p by del t. Of course, don't forget, when you are taking del v by del t, then you are del p by del t, then you are keeping v and n constant. In this case, you are keeping t and n constant. So like that, you can write Maxwell relation using these two equations as well. So it's very easy. You can write these Maxwell relations. And now we will come to the problems which we are going to solve. So I am going to take two problems. Okay, so this was the question which came for 1 point in GATE 2022. So here they have given 4 equations and they have asked you which one is incorrect. Okay, so by now you know what all these variables mean. Okay, so let's write down, because this is in A, so I am going to write down equation for A, that is equal to u minus ds, okay, and in differential form dA is equal to, okay, so I have told you how to write quickly. So I am changing my variable from s to t. So what I will do is, instead of writing TDS, I will write SDT, put a minus sign, nothing else will change, so it will be minus PDV plus mu dn. Okay, so I have written both the equations. Now let's use it. So del A by del B, okay, at constant t and n, del A by del V at constant t by del A by del V at constant t and n, that is nothing but equal to minus b. Okay, del A by del n, let's write that, del A by del n at constant t and v, at constant t and v, that is nothing but mu. Okay, so for two phases to be in equilibrium, their pressure, temperature and chemical potential are same. So P and mu are same. So that means in liquid and vapor phase, this quantity and this quantity, they are going to be same. Okay, this is P and this is mu. So these two equations are correct. let's look at the third equation, A plus PV. Okay, so A plus PV, that is equal to U minus TS plus PV, which is equal to G. We also know that when two phases are in equilibrium, then G is the same in both the phases. Okay, so this equation again is true. Let's see the final equation, A plus TS. A plus TS is equal to U minus TS plus TS. So that is equal to U. We all know that when two phases are in equilibrium, then their U is not same. Okay, so this equation is basically incorrect. So quickly, if you remember these two definitions, or you know how to write these definitions or these equations, you can solve this problem within a minute. So the second problem which I am going to take, it appeared for 2 points in GATE 2022. That is question 47, in which you have been given the values of beta and kappa. From your knowledge of thermodynamics, you know that beta is nothing but thermal expansion coefficient, and your kappa is isothermal compressibility. Now they have given the value of V, and at temperature equal to 4 degrees centigrade, they have asked you to calculate this partial derivative. Okay. Now whenever you see a partial derivative in S, you know that you have to use Maxwell relation. But which Maxwell relation to use? Usually what I do is, if I have some known quantities, okay, like say I have these two known quantities, okay, so I will first try to write a Maxwell relation which contains either this term or this term. Okay, so first of all what I do is, now which Maxwell relation to write, or which equation to write, from that you will derive your Maxwell relation. That I usually figure out by seeing these two. Okay, so this is T and P, so this gives me a hint. Okay, this gives me a hint that I should write the equation which is in a variable T and P. And which one is that? That is the equation of Gibbs free energy. Okay, so I am going to write dg. Now I have written, I have told you how to write these equations. Okay, since I am changing both S and V into T and P, so instead of writing TdS, I will write SdT with a negative sign. Then I will write V dP and plus mu dN. Of course, mu will not be used over here, so I can forget about it. Okay, so let's just erase it. Now if I write my Maxwell relation using this, it becomes minus del S by del P, del S by del P at constant T, that is equal to del V by del T at constant P. Okay, so what I see is that I have got Maxwell relation which contains this thing, and I know the value of this partial differential. Okay, so that tells me I am going in the right direction, but I don't have to find del S by del P. What I have to find is del S by del V. Okay, so in order to find out del S by del V, let's do one mathematical manipulation. Let's say if I write del S by del V into del V by del P, it's applying chain rule at constant T, that should be equal to del V by del T at constant P. From here, del V by del T at constant P is nothing but equal to V into beta. Okay, so that is V into beta. Okay, now I can just separate these variables, del S by del V at constant T, del V by del P at constant T. Okay, don't mind if I am using small v or capital V, then essentially I mean the same. Okay, so del S by del V at constant T into del V by del P at constant T, that is equal to V times beta. Now take a close look at this equation. Okay, now del V by del P at constant T, it's nothing but minus V times kappa. Okay, so instead of this partial differential, I can write minus V times kappa. So let's do that. So it is del S, okay, of course this is minus sign, I should retain over here. So minus del S by del V at constant T into minus V times kappa, that is equal to V times beta. Okay, I have to calculate this value. So what I will do is minus minus becomes plus, so don't have to bother about the negative signs anymore. V I will keep over here, and then what I get is V beta by kappa. So basically your differential which they had asked you to calculate, del S by del V at constant T, that becomes equal to V times beta upon kappa. Okay. Now, what is the value of beta? That is equal to 0. So immediately your this term, it becomes equal to 0. So you have seen, you have to quickly figure out which Maxwell relation you are going to use, okay, and then the whole question becomes very simple. So I hope you understood what I was trying to teach. If you like this video, please don't forget to subscribe and like. Okay, thanks a lot.